Okay, guys, so just continuing on from our discussion on metabolic pathways, what we want to understand in these multi-step processes is much like investing energy to your bike ride up the hill, right? You put energy in, all right, invested energy to enjoy the energy release of the descent, right, going downhill. And so in the same way, chemical reactions are coupled, right? So they're coupled by an energy investment in, or it doesn't always have to start with an energy investment in. It can start in lots of different ways. So you could actually get an energy investment out, right, of step one, and that provides energy to drive step two, and so on. And then maybe in step three, you have to put energy in again and get energy out in step D. And it all depends on the different reactions. You could have to invest, you know, in the first three steps of the reaction, you might have to invest energy to then down the road get a payoff of energy out. So we call this energy coupling, right? So the combination of energy in and energy out that occurs in metabolic pathways consisting of several, sorry, I'm running over top here, several individual reactions. Okay, so we refer to that as energy coupling. And we'll see again in chapter 6, we're going to see how some stages of cellular respiration involve this energy input, and the payoff phase comes out big time at the end. All right, so that's in chapter 6. The last thing I want to leave you with here in our discussion about energy in chemical reactions, I mean, where we're going with this, if you look here, we've got energy from exergonic reactions, right? So we've got energy coming in, and in our cells, most of this energy coming from chemical reactions. So when we get this energy out, we generally use that to drive the formation of ATP. So we get energy out from chemical reactions, and we use that to create this high energy currency that we can use anywhere, right? And at the same time, when we use this ATP and we break the ATP down, that process releases energy to drive other types of endergonic reactions. So it's this coupling phase, how we use the energy output to drive ATP synthesis, or the breakdown of ATP leads to energy release to drive endergonic reactions. And I show this picture of ATP over here to help remember and help you recall, one, that this is a molecule we should be able to recognize. So remember, it consists of the sugar here, which is ribose, and then we have this nitrogenous base, which is adenine. So it looks much like the nucleotide of nucleic acids. But the real big important part of this molecule are these three phosphate groups that are attached over here. And if I draw your attention to the electrons, you've got these negative charges in these phosphates, and on top of which you have electrons in these bonds. And I want you to think about that loaded spring, okay? So when you start to place a whole bunch of electrons together, right, these electrons want to repel. So what it means is that these bonds are high energy, unstable bonds. And again, high energy, unstable bonds. And it goes back to that concept of the potential energy stored in those bonds. And I use the analogy of, like, storing energy in a spring when we compress a spring. This is potential energy in the chemical bonds due to the position of electrons, right? Okay, moving on to our next page. All right, so at this stage in the game, we got to start understanding, the nature of the rate of chemical reaction. Okay, and so in order for our cells to do what they do and meet the demands of a multicellular complex organism such as ourselves, these chemical reactions have to occur quickly. So all these chemical reactions that we're talking about, these metabolic pathways, these series of steps, exergonic, endergonic, whatever these chemical reactions are, they have to occur at substantial rates in order for them to produce the amount of product that we need to keep the cell function and ultimately the organism. I want you to pause the video for a second, and I want you to think about this question. For cells to survive and for you to do what you do, reactions have to occur quickly. So how can we make chemical reactions go faster? What are some ways? And so obviously I think one of those I hope you put down, enzymes, but what are other ways that we can make chemical reactions occur more quickly? So pause the video, give it some thought, and then start the video to find out the answer. Well, if you came up with increasing temperature, increasing the concentration of your reactants, increasing surface area, or adding a catalyst or an enzyme, these are all factors that influence rates of reaction, okay? What I want you to understand about reactions is if we look at this picture over here, let's assume these two things that we have here, this is molecule number 1, this is molecule number 2, and in order for a reaction to take place, these things have to collide. They actually have to come into contact, they have to smash into each other. Think about the relationship between kinetic energy and potential energy. So that's what's happening in a chemical reaction. We have this exchange or this transformation where their movement, their kinetic energy, as they collide into each other, will be transformed into potential energy in the bonds as bonds are broken and new bonds formed. All right. So how does increasing temperature increase the rate of a reaction? Well, two things. One is when you increase the temperature, these molecules are going to have more kinetic energy. So that does two things. With more kinetic energy, they're moving faster, so they're going to collide more often. And because they're moving faster, well, think of a car. If you're driving in a car and you're going faster, if you hit something, you're going to hit it harder. So both of these both of these components increase the successfulness of a collision and a reaction. Increased temperature, particles move faster, collide more often, collide harder, and you get a greater chance of a successful reaction. The rate goes up, okay? Think about concentration and surface area. They're kind of concentration we refer to when molecules are in a solution. Surface area we include or discuss when things are in the solid form, okay? But both of them, they don't increase the speed of particles or how hard they hit, but you increase the number of particles there that could collide. So in a sense, if you think about dancing by yourself in the bedroom versus dancing in a mosh pit, when you're surrounded by tons of other people, well, you're going to have collisions, right? So if you increase the concentration, you're going to have more collisions. More collisions means greater number of successful collisions, and the rate goes up. So the goal in this section is to look at, well, what does an enzyme do? Okay, and so in order to get an idea, I want you to watch the video first. So you're going to pause this video and you're going to go to this video, which is on our course homepage in chapter 5 under the working cell. So if you click on the working cell and you scroll up to page 6, how enzymes work, and you click on that, you can see that video right there. So pause, have a watch, and then resume your notes. Okay, so here we are. So the long and short of what the video is trying to get you to understand is there's an entirely different way to help speed up a reaction. You don't have to make the molecules go faster. You don't have to increase the number of particles out there. What you do is you basically provide what we call a favorable geometry to the collision, a favorable geometry to the collision. okay? So if you think about it in terms of automobiles, if you think about a collision being a good thing, right? And you want to collide. Well, there's certain kinds of collisions that can give you the most bang for your buck, right? If you if you glance off, as two cars maybe sideswipe each other, that might not be a very effective collision, right? If you're a demolition derby driver and you really want to nail somebody, well, think of maybe a T-bone, think of a head-on. There's certain ways that give you a more or there's certain orientations that give you a more effective collision. Well, this is true for particles as well. So think of, here's our molecule 1, here's our molecule 2. Let's imagine this collision where they hit in the middle. This might not be a very effective collision if they hit here, because it's maybe these particles out here that need to collide with each other. So colliding here doesn't give you an effective result, okay? Or sorry, I guess according to the picture here, this is the one we want to be effective. Reaction occurs. So colliding in this manner gives us the best possible outcome or best possible result. If the molecule collides from this end, or if the molecule collides here or here, these just simply aren't effective collisions in terms of what the end result is expected to be. So where do enzymes come into this? If you recall from the video, enzymes have unique shapes that allow them to bind onto the reacting molecules and orientate them in such a way as to provide that favorable collision. Okay, so what we're going to do is I'm going to pause. That's our second 12 minutes. I'm going to pause that, and then I'll do the third installment of your notes.